sky above us is undergoing a silent, profound revolution. Unmanned aerial vehicles, once simple remote-controlled tools, are rapidly evolving into highly autonomous, cognitive entities known as Agentic AI systems. This marks the dawn of autonomous aerial intelligence. Operating within a vision-language-action paradigm, these agentic drones continuously execute complex sense, think, act loops to navigate unpredictable, dynamic, and potentially hostile environments. To achieve true autonomy, a drone must first master its own complex kinematics. Predicting an aircraft's exact four-dimensional trajectory, encompassing longitude, latitude, altitude, and time, is an incredibly challenging mathematical problem. Advanced architectures like attention-enhanced long short-term memory networks decode this complexity. They extract deep time series features from flight data, instantly compensating for severe wind disturbances and unpredictable aerodynamic resistance. By integrating Euclidean Signed Distance Field gradients, these neural networks ensure that planned flight paths remain dynamically feasible and entirely collision-free, even at high speeds and densely cluttered environments. Yet, safely navigating three-dimensional space is only the baseline. Agentic UAVs must actively perceive and track dynamic targets on the ground. This introduces the profound computational challenge of visual occlusion. In dense urban canyons or thick forests, targets frequently vanish behind obstacles. To combat this, researchers use advanced vision transformers and dilated wavelet receptive field enhancements to maintain tracking logic. Algorithms like OMCTrack utilize adaptive motion compensation. They mathematically predict a target's hidden position, seamlessly bridging the gap until the object reemerges, all without losing the target's unique digital identity. But what happens when optical conditions degrade entirely? During heavy fog, extreme atmospheric interference, or nighttime operations, standard visual tracking algorithms suffer from severe data degradation and catastrophic failure. The ultimate solution lies in multimodal sensor fusion. Next-generation drones integrate thermal imaging, LiDAR point clouds, and highly sensitive directional acoustic arrays into dynamically weighted graph neural networks. Through acousto-optical hybridization, an onboard AI dynamically calculates confidence scores for each sensor stream. It prioritizes the most reliable data, maintaining absolute situational awareness in total darkness or adversarial camouflage. In modern defense and aerospace security, perceiving a target is just the beginning. The intelligence system must move beyond knowing where an object is to mathematically deducing exactly why it is there. This is a specialized domain of hostile intent recognition. Deep neural networks, such as the Attention-Enhanced Contrastive BiLSTM, continuously evaluate the underlying tactical sentiment of an approaching object's flight path. By analyzing microscopic maneuvers, sudden acceleration spikes, and path tortuosity, the AI classifies the target's true objective. It can perfectly distinguish a lost civilian drone from a coordinated, hostile perimeter probe. Even under severe information uncertainty or active electronic jamming, these cognitive models can mathematically reconstruct missing telemetry data, granting ground commanders critical minutes of proactive early warning. The ultimate paradigm shift unlocks when individual drones merge into a decentralized swarm. Here, single aerial units become interconnected nodes in a vast, floating, and highly resilient computational brain. Governed by multi-agent reinforcement learning, drone swarms exhibit profound collaborative intelligence inspired by apex predators. They execute highly synchronized tactical maneuvers without relying on a vulnerable central command server. Utilizing graph convolutional networks, the swarm communicates via dynamic topological maps. They share spatial beliefs in real time, instantly and autonomously reallocating tasks if a single swarm member is intercepted. During adversarial pursuit evasion games, the swarm calculates multidimensional capture cones. They execute flawless flanking techniques and serpentine encirclements to effectively neutralize highly evasive and unpredictable targets. Managing such immense tactical complexity requires a revolutionary interface between humans and machines. Today, this cognitive bridge is forged through the integration of multimodal large language models directly into the drone. A human operator can issue a simple natural language command, such as secure the southern ridge and track any hidden vehicles. The onboard AI instantly decomposes this abstract concept into actionable mathematics. The vision language model maps semantic human language directly onto visual and spatial awareness. The drone autonomously selects its optimal flight routes, sensor configurations, and cooperative task assignments for the swarm. We're standing at the very threshold of a new aerial epic. The seamless integration of deep trajectory, clustering, intent recognition, and swarm intelligence has fundamentally redefined the limits of autonomous robotics. These cognitive aerial agents have transcended their initial, rigid programming. They no longer merely observe the world below, they actively understand, predict, and shape the absolute future of global security and logistics.